I'm on a camping trip right now, and the agenda today consists of canoeing. Although, before I can actually go canoeing, I have to get to the lake. And following this trail to the lake has made me wonder, is this trail the fastest way to get to the lake? Or is there a faster way? And how could I figure that out? Hi, I'm Annika, a second-year student studying creative technology and design at CU Boulder. And to figure out if I'm on the fastest route, let's learn about how the relationships between shapes and angles can help us get places. When we're getting around today, there are a lot of different things we can use to know where we are. We have technology like GPS and phones that can determine route and position for us. We have signs posted all around cities, street signs, building signs, and so on, that we can use to figure out where we are. And even if we were somewhere without a sign, we can use landmarks like cool rocks or big trees to keep track of where we've been. However, what if we were traveling into the ocean, where there's nothing but the sky and sea to guide us? We talked about a few methods of travel in our last video about navigation. But what if we wanted to get really specific about distance and find the fastest route somewhere rather than just a route? Well, surveyors, who are engineers that can determine very exact distances on, near, or beneath the surface of the Earth, have the solution. And that solution is triangles. Triangles are shapes with 3 sides and 3 angles. If you were to add up all of the angles of any triangle, they'd always equal 180 degrees. We categorize triangles based on their sides and angles. We have 3 names for triangles based on how many of their sides are equal. A triangle where all 3 sides and all 3 angles are equal is called an equilateral triangle. Since we know the angles of a triangle always add up to 180 degrees, and a triangle has 3 angles, then we know that all 3 angles of an equilateral triangle are 60 degrees, because 180 divided by 3 is 60. A triangle with 2 equal sides and 2 equal angles, which are the angles opposite the equal sides, is called an isosceles triangle. And a triangle with no equal sides or angles is called a scalene triangle. We also have 3 names for triangles based on just their angles. An acute angle is an angle that's less than 90 degrees. If we have a triangle with all 3 acute angles, then we call it an acute angled triangle. An obtuse angle is an angle that's greater than 90 degrees. If we have a triangle with just one obtuse angle, then we call it an obtuse angled triangle. We can't have more than one obtuse angle in a triangle, as having 2 angles over 90 degrees would mean our angles don't add up to 180, which means we don't have a triangle. If we have an angle that's right in between an acute and obtuse angle, meaning it's exactly 90 degrees, then we call it a right angle. And, as you can probably guess, a triangle that has one right angle is called a right-angled triangle, often shortened to a right triangle. And when it comes to figuring out distances, right triangles are extremely important. Because if you have a right triangle and you know either 2 side lengths or 1 side length and one of its angles other than the right angle, then you know everything about that triangle. And how exactly do we know everything? Let me show you. Right triangles have a lot of special properties relating their sides and angles to one another. The first property is summed up with the Pythagorean theorem, which states that in a right-angled triangle, the area of the square on the hypotenuse equals the sum of the squares on the other 2 sides. To understand this, let's draw a triangle. We're going to represent each side with a variable. Let's call the hypotenuse, which is the longest side of a right triangle, and the one opposite the right angle, C, and we'll call these other 2 A and B. The Pythagorean theorem states that the area of a square on the hypotenuse meaning the area of a square with the hypotenuse as its side lengths, so c squared, equals the sum of the squares on the other two sides, so a squared and b squared, added together. That gives us the equation of a squared plus b squared equals c squared, which is the Pythagorean theorem. We can use the Pythagorean theorem to find a missing side length of a triangle, assuming we know 2 already. But what about the angles? Or what if we only know one side length and one angle other than the right angle, like I mentioned before? Well, that's where the building blocks of trigonometry come in. But first, we need to talk about angles, because there are actually 2 different ways we can measure an angle. The first way is in degrees, which we've been using so far. Degrees measure the amount of rotation between 2 lines. A full rotation, meaning the lines are overlapping and thus would be drawing a circle, is 360 degrees, and we use this little circle symbol to show that a measurement is in degrees. The second way we measure angles is with something called radians. A radian is the angle made when the radius of a circle represents an arc on its perimeter. So, if you were to take the line that is the radius of a circle and wrap it around the edge of that circle, the angle formed by drawing 2 lines from the edges of our arc to the center of the circle is 1 radian. Mathematicians have figured out that the angle of a full circle in radians is actually 2 times pi, or rounded to the nearest hundredth, 6.28 radians. Therefore, 180 degrees is pi radians. 1 radian is about 57.3 degrees, and 1 degree is about 0.017 radians. When we're doing trigonometry, there are certain functions we use a calculator for, and calculators can accept measurements of angles in either degrees or radians. Thus, it's important to know which kind of measurement you're using to set the calculator in the right mode, so your calculations aren't totally thrown off. Which, speaking of trigonometry functions, let's actually learn about those functions, shall we? Trigonometry is a branch of math dealing with the relationships between the angles and sides of triangles. When we're looking at a right triangle, we already know that the longest side is called the hypotenuse. However, when we're looking at a triangle through the lens of trigonometry, we have names for the other 2 sides too. Those names move sides depending on which of the 2 angles that isn't the right angle we're focusing on, though. So for now, let's focus on this one. We call the side that is attached to this angle and not the hypotenuse the adjacent side. We call the side that isn't attached to the angle at all the opposite side. So, while focused on this angle, this side is the opposite side, this one's the adjacent side, and this one's the hypotenuse. If we focused on this angle, the opposite and adjacent sides would switch names. Now that we've named our sides, let's learn how they connect to each other and to the angles. We have 3 main relationships to look at: sine, cosine, and tangent. And we can remember these relationships with the acronym SOHCAHTOA. First, SO. SO stands for sine equals opposite over hypotenuse. What this means is that the sine of an angle, written like this, where that circle with a line is theta, which is a special variable we use for angles, equals the length of the opposite side divided by the length of the hypotenuse. Second, CA. CA stands for cosine equals adjacent over hypotenuse. So, the cosine of an angle equals the length of the adjacent side divided by the length of the hypotenuse. And finally, TOA. TOA stands for tangent equals opposite over adjacent. So, the tangent of an angle equals the length of the opposite side divided by the length of the adjacent side. To use these relationships to find a value, we first have to determine which equation to use based on what information we do and don't have. Let's say we're looking at this triangle and trying to find all of the angles and sides. We can find the value of angle x because we know all three angles add up to 180, so we plug in our values and solve for the missing variable. Now, let's find this side based on angle y. Our missing side is the adjacent side to angle y. The other side length we know is the hypotenuse. Based on SO, CA, TOA, which one uses the adjacent side and the hypotenuse? Cosine does, because cosine is adjacent over hypotenuse. So we plug in our values and use our calculator to solve for our adjacent side, and get that that side is 8.192. Then we can find our final side length similarly using angle y. Now our missing side is the opposite side, and since we know the length of both the adjacent side and hypotenuse, we can choose either sine or tangent to solve for our missing side, getting 5.736. So now we know the basics of trigonometry. But how can we use that to find a distance? Well, let's say you're trying to measure a river without crossing it. First, we need to find something on the other side of the river to represent a point of our triangle. Let's say there's a tree. We'll call that our first point. Now, we need to line up directly across the river from the tree. Where we're currently standing is the second point of our triangle, and the imaginary line between that point and our tree is our first side. Now, we're going to draw another side at a right angle from the point we just made. We'll do this by walking perpendicular to our first side, and make sure to measure the distance as you walk. Wherever you stop is our final point. You can measure the angle at that final point, and oh, look! We now have a right triangle with one known side length and one known angle that isn't the right angle. And thus, we can use our trigonometry to find all the other information about our triangle, including the distance across the river. We can apply this method to any situation. As long as you can identify a point, line up with that point, walk perpendicular to the imaginary triangle's first side, and measure the distance you walked and the angle the original point is now at, you can determine a distance. And just like that, we now have the secret tool for finding distances: right triangles and trigonometry. With these tools, we can determine unknown distances. And since the fastest way to get somewhere is a straight line, we can also use our triangles to find the fastest route. Speaking of the fastest route, I better figure out what the fastest route is to this lake so I can go canoeing. Thanks for following me down the road of trigonometry, and until I see you again, keep on exploring the world of engineering. Check out the full lesson on TeachEngineering, then use what you learned in the associated activities, stay in shape, and trig river.